So at the start of chapter 12, they discuss a relationship between lead exposure and IQ scores. And we've discussed this a little bit ourselves, especially in light of what's happened up in Flint. And what they have here are various samples of people and their lead, low blood levels, medium blood lead levels, high blood lead levels, and their sample IQs. Well, what we've done up to now is sometimes we've worked with one population or two populations and compared their mean, or tried to see if the means of two populations were equal, etc. But what if you have more than one population mean to deal with? Then what do you do? If you have 3 or 4 or 5, etc. We can have as many as we want, but when you're comparing means across multiple populations, you have to do something different. And that something different is called an analysis of variance. So that's the test we're going to work on in chapter 12. So analysis of variance has a very clever acronym. It's called an Anova. So in an Anova test, this is your null hypothesis, that the mean from group 1 is equal to the mean from group 2 is equal to the mean from, perhaps I should say, population 3, etc., all the way up to k, where k is the number of populations that you're comparing. So all these are equal is your null hypothesis. And then your alternative hypothesis is that at least one of them is different. One of them doesn't match the other ones. So it's called an omnibus alternative. It's like a catch-all. It's like everything. At least one of them is different. To figure out which one is different and how different, you'd have to do some follow-up analysis. We're going to limit ourselves to just working on this part, deciding whether or not we reject or fail to reject the null hypothesis. Briefly, the way this works is you set up an analysis of variance table. And again, this is something they may or may not ask you to fill out. But what happens in the analysis of variance table is you look for sources of variation. And you compare the variation within a group to the variation outside the group. You have what's called the treatment sum of squares and the total sum of squares. Variation within the group and variation outside the group. And then you form a ratio of these two things that gives you what's called an F statistic. We've dealt with the F distribution before, and it comes from the ratio of two chi-square variables. The rest of this is the same. You can see that I've been redoing my handouts a little bit to try and include some stuff on Statistic, how you do these. Go to analysis, one-way analysis of variance. Now there's some assumptions that go along with the analysis of variance test. And they're too long that I didn't want to bother putting them into the handout, but they are in your book. One thing about an intro stat class, I can't spend too much time and effort, really being dogmatic about using the requirements and checking the requirements. But once you leave this classroom, before you do these tests, you should make sure that these requirements are satisfied. So one of them is that the populations have to be distributed approximately normal. This one's one you can kind of wink and nod at, especially if you have large sample sizes. Then you should be okay. Another one is that you have equal variances between the populations. Again, this is not too bad as long as your samples don't vary by too wide of an amount. Then a couple more sample requirements: simple random sample, independent samples. So you can't sample in the before and after case. This would not be some place to do something which leads to dependent data and populations that are categorized in exactly one way. So those are all those assumptions here. Let's apply this to a couple examples. And let's start with problem number 12. 12 looks, well, trying to find one that doesn't look like it's going to take too much data. I guess we'll do problem number 14. Weights of poplar trees were obtained from trees planted in a sandy and dry region. The trees were given different treatments and identified in the table below. The data from a study conducted by researchers at Penn State University and provided by Minitab. Use the 5% significance level to test the claim that the 4 treatment categories yield poplar trees with the same mean weight. Is there a treatment that appears to be most effective in the sandy and dry region? So, okay. What we're going to do is we're going to enter this data into separate columns of StatDisk. So, let's do that here. Clear out some old data. Bless you. So treatment 1, basically no treatment, 0.24, then 1.69, 1.23, 0.99, and 1.80. In our next column, let's put in 0.92, 0.07, 0.56, 0.56, 1.74, and 1.13. In column 3, the irrigation column, we've got 0.96, 1.43, 1.26, 1.57, and 0.72. Last column, the fertilizer and irrigation column, we've got 1.07, 1.63, 1.39, 0.49, and 0.95. Now the null hypothesis is that all 4 of these treatments, or non-treatment in the case of the first one, lead to the same mean weight. So let's get busy on stating our null and alternative hypothesis. And let me do that over here. Problem 14. The null hypothesis is that the mean from, oops, let's zoom out a little bit. The mean from no treatment equals a mean from fertilizer. Oops. Equals a mean from fertilizer equals a mean from irrigation equals a mean from fertilizer and irrigation. So all 4 of these treatments, or non-treatment in the case of the first one, are the same. The alternative hypothesis is that at least one of them is different. So at least one of the above means is different. We're going to test this claim at the 5% significance level. We've already input our data, so let's go back and do some analysis. So typically when we go to do analysis, it's right underneath this tab, Analysis. We want to find one-way analysis of variance, which is just above midway down. And then it's going to ask you to indicate what columns we're going to use. This is much like we did with the last section. So we want the first 4 columns. Significance level of 5%, so evaluate. Now, I haven't explained a whole lot about what analysis variance is and how you conduct it. You should have a good idea of the fact that we're testing for the equivalence of these 4 means, and that our null hypothesis says that all 4 of these means are equal, that they come from a population where all 4 of them are equal. Can we reject the null hypothesis? Should we reject the null hypothesis? No. Yeah, it's really high. It's nowhere close to being able to reject. So, if you were looking at the results of this study and deciding what you wanted to do with your poplar trees, is it worth it to fertilize, irrigate, or both? Are you producing a mean for one of these that's significantly different than this one? No. So, no, it probably wouldn't be worth it to fertilize or irrigate. At least not according to this data. So, fail to reject, H naught. There is not sufficient evidence to warrant rejection of the claim that the treatments are the same. There is not sufficient evidence to reject the claim that the mean weight of poplar trees is the same. If you did find a significant difference, what you could do is you go back and do some follow-up analysis and try and find confidence levels of where you think the mean of one treatment is. In fact, you can find confidence levels for all 4 of these. And what you should see in this particular case is that those confidence intervals should all overlap. They should have some values in common, which means that somewhere in that common area is probably where the true mean yield is for this kind of experiment. But they should have a common value, otherwise the Anova test should be leading us to the rejection of that claim. Okay. Let's do another one. Are we okay with problem number 14 here, this first one? let's take a look at problem number 12. It's going to involve a little bit of data input. On an exam, I'm not going to ask you to input a lot of data. I don't want you to get problems wrong because you made a typo, etc. So I will have data ready for you. Pages are randomly selected by the author. The Bear and the Dragon by Tom Clancy, Harry Potter and the Sorcerer's Stone by J.K. Rowling, and War and Peace by Leo Tolstoy. The Flesch Reading Ease score for these pages are listed below. Use a 5% significance level to test the claim that the 3 samples are from populations with the same mean. Do the books appear to have different reading levels of difficulty? So, okay, well, let's find out. So we're going to have to input a lot of data. Let's go back to Statistic. Actually, you know what? Before we do that, let's write down a null and alternative hypothesis. So problem number 12. So mu for us is going to represent the Flesch reading score. So we'll call it mu sub Clancy equals mu sub Rawlings equals mu sub Tolstoy. The alternative hypothesis is at least one of these is different. By the way, not that it's really going to come up, but you could technically do an analysis of variance if you just had 2 populations. But what's going to happen is that it's going to be equivalent to the same thing that you would get if you did a t-test for the difference in 2 populations. So if you just have 2, it's probably just as easy to do a t-test as opposed to an ANOVA. We're going to do this at the 5% significance level. And beyond that, you have a lot of data to analyze. One thing's very, very important here. That is, the data is set up a little bit differently than our last one. You have to enter the treatments in different columns. So even though the data is listed across rows, you really have to write it in columns. So what you have to do is you have to write all of Clancy data in column 1, Rowling in column 2, Tolstoy in column 3. So you can't just copy it as is. Basically, you got to kind of turn it on its edge like that. They have to be in separate columns. So a nice little thing to note as we input our data. All right, so somebody make sure that I'm putting in this in honestly. 58.2, 73.4, 73.1, 64.4, 72.7, 89.2, 43.9, 76.3. I don't think you just put any of those. Oh, are you kidding me, man? Wow. I was in the zone, man. I'm like, oh, I'm jamming it. Why did these not go in here? All right. Great. And of course, I got this recorded too, even better. All right. 58.2, 73.4. Oh, man, this is just really, really bad. Well, let's do this. Window, no, datasets, 12th edition. Does it have these things here? No, I don't see it. Body temperatures. It would have been nice. Yeah. All right. Yeah, I don't think we're going to get so lucky. All right, let's try it last time. Otherwise, we're just going to quit and go home. 58.2. Yeah. Believe me. So I got a lot of people cheering for a misstep here. 73.4, 73.1, 64.4, 72.7, 89.2. I'm definitely making a mental note next year to, when I teach this again, not to do this problem. 76.3, 76.4, 78.9, 69.4, and 72.9. Get the oxygen brought out. All right. Wrote column 2, 85.3, 84.3, 79.5, 82.5, 80.2, 84.6, 79.2, 70.9, 0.9, there we go, 78.6, 86.2, 74, and 83.7. So one of the things this illustrates is what a pain it is to get data in and get it in correctly. In college, I had a job that I had to check the data was entered correctly. And basically what we did was we double entered it independently and then went back and matched the data. And where there was discrepancies, you had to figure out, well, what was the correct data. All right, so 69.4, 64.2, 71.4, 71.6, 68.5, 51.9, 72.2, 74.4, 52.8, 58.4, and 65.4. Oops. 65.4, and finally 73.6. It took way too long. All right. But again, you know, it's a real shame if you've made a mistake entering your data and you spend all this time to collect your data, and then your analysis can be off. So you really want to take good care entering your data. I think we're ready. We're going to do our analysis now. So analysis down to one-way analysis of variance. Columns 1, 2, and 3. We're doing this at the 5% significance level, so let's see how we do. Wow, so all the way down to the p-value. That's the one that we need to catch our interest. 0.0005. Kylie, what should we do with our null hypothesis? Should we accept or good? Fail to reject or reject? Yeah, we're going to reject. So the Anova test is based on the F distribution. If you were to plot this, what you'll see from the F distribution is that the borderline of what you should expect for this test to be, you know, somewhere between accept or fail to reject and reject is right here at 3.285. Our observed value for this test statistic was way, way past that. And correspondingly, our p-value, which is a probability of getting something this extreme or more extreme, is really, really small. We've got a p-value of 0.000562. So that's way less than alpha, 0.05. So we reject. So what's that saying? Well, it's saying that there's a difference in these means. That the reading levels are not all the same for all three of these. In words, there is sufficient evidence to reject the claim. I think the author is fond of using the word warrant. Warrant rejection of the claim. That the three books have the same Fleisch reading score. Let's go back and do a little follow-up analysis with this one. So let's go back to our table and close that out. And let's find some confidence intervals for each column of data. So let's go back to analysis. Way back down, several chapters ago to confidence intervals. We want to find a confidence interval for a mean of one sample. Now there's some nuances about this that I'm not going to explain, but let's just take a look at what all these confidence intervals would look like. So a mean of one sample, we're going to use data from column 1. We don't know the population standard deviation, so we'll leave that blank. We get a confidence interval somewhere between 63.54 and 77.93. And that's for column 1. That was the data from Clancy. So Clancy, 63.54 and 77.93. Let's repeat that for the other two columns. For column 2, between 77.78, this is what column 2 was Rowling. $77.78 and 83.72. And last but not least, Tolstoy. So that's in column 3. Let's click evaluate here. So Tolstoy, 61.15 less than mu sub t less than mu sub, or less than 71.14. Now I'm not sure, but I think that these I'm calling it Fleisch because I'm just not really fond about saying flesh, but it does look like flesh. These reading scores, I think, are lower the harder it gets. But let's take a look at our data all together. Notice how there's not really much overlap here, right? I mean, if you just look between Clancy and Rowling, wow, there's very little opportunity for these things to overlap and both be true. They're almost completely apart from one another. And Tolstoy, that one doesn't fit in all of these either. Basically what this is saying is that there's not any particular value that could satisfy all three of these at the same time. So that's why we're rejecting the null hypothesis. This can't be true. The confidence intervals don't really line up to allow this to be true. Now, it's really not fair that I did it exactly like this. There's something called the Bonferroni correction factor that you'd have to throw in there, but that goes beyond this course by a considerable amount. What I wanted to do here was remind you of our confidence intervals and help you make sense out of this a little bit more. It doesn't look like these things should match. They should all line up. And in fact, that's what we concluded based on our analysis of variance test. Yes, sir. Max.
If there is like a tiny overlap between all three, would you then not be able to reject them?
You wouldn't be able to exactly do what I did here and make that conclusion. So basing your conclusion off of the confidence intervals the way we did it wouldn't be right. You wouldn't be able to do that. And the reason for that goes a little bit beyond the class. But basically what's happening is that you have to account for adding up different type 1 errors. And that would change the width of your confidence intervals. Yeah. So, all right, but I appreciate the question. Anything else on problem number 12 or analysis of variance in general? Okay, so for homework, try 1 through 15.